And now onto my presentation. So in this session, we will talk about Java in the cloud with GraalVM and how GraalVM can actually help you make your Java applications ready for the cloud and more efficient in the cloud. And a few words about myself, because this is actually my first time speaking at this conference here in Amsterdam. So I'm Alina, this is my Twitter handle. So if you have any questions that you would rather ask privately in DMs, my DMs are open, so feel free to. And I'm a developer advocate for GraalVM at Oracle Labs. And Oracle Labs is this cool R&D unit at Oracle where we're doing a lot of research, creating many projects from scratch. And we usually work in domains such as programming languages, compilers, machine learning, security, etc. So we are doing a lot of cool research stuff. And I also love open source and communities, and I'm very happy to work on GraalVM because it's also a huge open source project. So I'm very proud and happy to be working there. And I love both programming and natural languages. I cannot say that I speak much Dutch, but I'm open to learn it if you will give me a couple of lessons. And I'm also Ukrainian, and what you can see here on the slide is my beautiful hometown, Lviv. So if you ever have a chance to travel to one city in Ukraine, I recommend that you go straight to Lviv because it's beautiful and amazing, and I hope that you will like it as much as I do. So now let's talk about Java and the cloud and GraalVM and how it all fits together. So first thing, I want to give you a brief overview of GraalVM because it's a huge project and there is so much you can do with it that it's sometimes confusing what exactly it is and where you can use it and why. And it's a good challenge to have, right? That there are so many things you can do with it, but still it can be a bit confusing. So let's get that out of the way. So one thing with GraalVM is that it can act as a normal JDK. So maybe you're using OpenJDK or any other JDK distribution, and GraalVM is a JDK just like that. And underneath, as a platform, it's using Hotspot VM. So the same Hotspot VM that you get in any other JDK distribution. And the only thing that is different is that we are replacing the top-tier optimizing compiler. So in Hotspot VM, that is the C2 compiler. And what we have is our own GraalVM compiler that is highly optimizing, brand new, and many applications will see additional performance benefits just by switching to GraalVM as a JDK. Now, another big part of the GraalVM, and that's the part that we will focus today in this talk, is native image. And that is this part of GraalVM that allows you to take your Java application and compile it ahead of time into a platform-specific native executable. So then you can deploy it on a machine that doesn't have any kind of Java runtime on it, and it will be fully functional, fully working on its own. And last but not least, it's also a polyglot VM. So far we talked about Java, but in addition to Java, it can also execute all those other languages, such as JavaScript, Python, R, etc. And the best part is that not only it can execute one of those languages, but it can also act as a polyglot VM, giving you a way to execute applications that use any mix of those languages. And it will give you those interop capabilities, but also performance optimizations for the whole thing out of the box. So that's the overview, but let's talk about Java specifically, because I do assume most of the people here are Java developers in the room or work with Java in some way. Okay, good. And how many of you have tried GraalVM so far? Okay, I would say roughly the half. I hope maybe a few more of you will have motivation to try it after this talk. So let's talk about what's in GraalVM for Java developers. So one thing is this just-in-time compilation mode, so your normal mode of executing Java applications where you can use GraalVM as your JDK and run your Java applications as you always would with the Java command. But in addition to that, GraalVM brings this whole new ahead-of-time execution mode for Java applications where you compile them at build time ahead of time, and then you run them as native applications when you need to run them on runtime. And this second mode of execution, ahead-of-time compiled applications, is really great for cloud deployments, because for cloud deployments, you want to accomplish fast startup, low memory usage, and that's exactly what you get with native applications. So in this talk, we will focus on this ahead-of-time native image compilation part. And what is also great about GraalVM and native image is that because it gives this fast startup and low memory footprint of native execution, it's widely adopted by many Java microservice frameworks. So if you're doing Spring Boot, if you're doing Micronaut, Quarkus, Halidon, all of them support GraalVM native image and give you an easy way to build applications with GraalVM. So talking about those frameworks, I think yesterday there was Holly's session about Quarkus, and she told me she mentioned GraalVM a couple of times there, so make sure to check that out. And also I mentioned that later in the talk, but right after this talk and after the break, there is Graham's session about Micronaut. So Graham is the creator of Micronaut, so make sure you check out that session as well. Long story short here is that all those frameworks will work nicely with GraalVM Native Image, and they give you an easy way to build GraalVM and Native Image friendly applications. So let's talk about Java in the cloud and what are the goals there and how GraalVM can help you meet those goals. So one thing you probably want to achieve in the cloud is to start fast, because if your application starts fast, it means that it can scale more easily, right? Because adding new instance is more smooth, more fast. But also it means that it's better for your users, because if your users need to wait a couple of seconds for your application to start, probably this is not ideal, and this is something you would want to fix if you have a way to do so. Now, another thing in the cloud, and I would argue maybe this is even more important, is reducing resources usage. Because in the cloud, you're paying for the resources that you're using and also for how long you're using them. So if you can deploy the same application, but in a way that it's using less resources or for less time, that would reduce your cloud cost. So you can either pay for it less, or maybe you can use the same infrastructure, but to deploy more applications. So this could be another goal you could be having. And minimizing vulnerabilities is a goal that we probably have no matter where we deploy applications, but it applies to the cloud as well. And we'll also talk about how GraalVM and Native Image specifically can also make your applications more secure. Last but not least, you might want to optimize for compact packaging size, because this means that you can have smaller, more compact images that once again are easier to scale, but also easier to deploy. And if you can reduce this packaging size, that will also be a great goal for the cloud. So let's see how GraalVM fits here and how it can help you achieve either of those goals. And for that, let's talk about this whole native image ahead of time compilation, because it's kind of non-trivial and very interesting how you can even take something so dynamic as a Java application and compile it ahead of time at build time. So the way this works, the way we turn Java applications into native executables, is that when you run our native image command and you give it your application, your Java application in a bytecode format, what happens is the following. So native image will look at your application starting from its main entry point, and it will try to find all the reachable code. So all the code that is needed for your application to work, to perform whatever the tasks it is supposed to perform, it will try to find all that code, and that applies to your application code, but also to all the dependencies that you are using and even the JDK classes themselves. So it will try to find everything that is reachable, so that then it can eliminate everything else and only put what is needed for your application into this produce native executable. And this way, by eliminating everything else, it makes this native executable very slim, very efficient. So only the things that are needed for your application will be included in the native executable. So this reachability is one part of the story, and there is another interesting part, and that is that we are also performing heap snapshotting. So as we are building your application, we are also preparing kind of a snapshot version of your heap, so that your application, when it starts, can start with pre-populated heap and not spend time and resources on putting those objects onto a heap. And that's another way how GraalVM and Native Image makes your application start fast, but also use fewer resources. So what you get in the end is a native executable with the machine code for your whole application and everything that is needed for it to run. And we are used to having the hotspot VM so that it provides us kind of VM functionality and VM features at runtime. In this case, you don't have, when you actually run the application, you don't have hotspot VM anymore, but you do have some VM, kind of basic VM functionality, and that is coming from a basic slim VM implementation that we are putting inside the executable. It's called Substrate VM, so we get some basic VM functionality, but you no longer need a full-blown JVM to execute your code because it's a native executable in the end. And let's compare those two modes of execution. So running on a JDK, so it can be GraalVM, OpenJDK, whatever JDK of your taste. So running on a JDK versus running on ahead of time compilation on native image. So the way those two different modes are different in terms of startup time is the following. When you first run your application on a JVM, you start a new application. What needs to happen is quite a few operations. So for your application to run and run at some point with peak performance in a fully compiled mode, there are the following steps. So you need to load your classes. You need to start interpreting, and interpretation is a nice, easy way to go from loading your application to actually executing your code. It's much faster in terms of getting your application to run than compilation, but also interpreted code is slower. So while you are in the interpreted mode, your application is not as fast. That's why the JVM is collecting information about your application, and it's trying to get to the compilation step, and interpretation is there to get to execute your code faster. But then initially, as it's performed all those operations, collected profile information, and compiled the application, at some point when it warms up and it's done with all those steps, your application can actually run with the best peak performance. But you can see that this has taken probably a while, especially if you have a larger application. Now, if we are compiling ahead of time to a native executable, what needs to happen in terms of startup time is just the following. So you are loading executable, and you can immediately start running your application and do this valuable job, because all of those steps were already performed when we were building your application. And this is the idea of this ahead-of-time compilation, that we are taking all those operations of code, loading, analyzing, compiling, profiling, etc., and we are moving them from runtime to build time, because usually you have a bit more time at the build time, but also more applications are started more often than they are built. So it kind of makes sense to do all of this work once at build time, and then start much faster every single time at startup, because we are no longer doing those kind of overhead operations. So that was startup time. And also let's talk about resources usage, because you can hear that, okay, startup time is great and it's interesting, maybe for microservices and serverless applications, but what if I have a long-running application that doesn't start that often, and maybe I don't care about startup time that much? And it indeed can be the case. And in that case, let's also compare how much memory we are using if we are running in either of those modes. So if you're running on a JVM in the JIT execution mode, you would need to keep around memory for your application itself, but also for all of that infrastructure that is there to execute your code. And it's a very powerful code execution infrastructure, because if you're running on a JVM, it can optimize for the best peak throughput, it can de-optimize, it can collect profile information. It's very powerful, but it also has this kind of memory impact and memory footprint. While when we are running on a native image mode, you need way less memory, because you are no longer dynamically executing code at runtime. And this gets even more interesting if you want to scale such an application, because if you're scaling on a JVM, you would need to also kind of gradually, proportionally scale memory for all this code execution infrastructure, while on native image, you are only scaling the code for the application payload itself. And to make this even a bit more visual, here we are scaling a Quarkus application by adding more instances of it. And the yellow bars, that is executing in JIT mode, so on hotspot VM, and the red ones, that is executing on GraalVM Native Image. And you can see that in both scenarios, we are kind of using a bit more memory over time, but way less memory on the native image, because it doesn't need that much memory, but also because some of the things are shared between native image processes as native applications. Okay, and I think this is enough of the slides. Let's see some code. So I want to show you a demo of running the same application on a JVM and in native image mode, and we will compare a number of metrics there. So let me get here. Which one is this? All good. So this is, as you can see, a Micronaut application, but this could have been any other framework. It doesn't matter that much. I used this one for the demo. So this is my Micronaut application, and it basically just starts my app, and I have a controller here that exposes a hello endpoint, and we will run this thing in both modes. So let's run it on the JVM first, and this is a Micronaut app, so I can just do the following. Okay, it's starting, and it said that it started in something like 560 milliseconds, and it's running on 8080. So let's go over there and check it out. Okay, it returns our hello GoTo, seems all fine, it's working. So let's kill this one, and also let me move it a bit higher and clear this. So that time we were running on a JVM, and we also have already a compiled version of this application in my target directory. So it's this simple REST native executable over there. So that previous process where we are running on a JVM, it's killed, it's dead, but I will use the same port, so let's run it again. So now I will run it as a native app, target simple REST, and we see that this time our application started in 20 milliseconds, so what, 25x faster than before. But don't take my word for it. Let's go and check that it's really running and it's really doing what it's supposed to be doing. So localhost hello. Okay, what's wrong? Okay, now it's on. Maybe there was a glitch in my connection, but yeah. Anyway, it's on and it's doing the same thing. But here we were looking at the startup time, and the numbers that we see here are reported by the framework. So maybe we want to do our own little benchmarking. Maybe we don't trust the numbers that the framework is reporting. Maybe we want to measure those things ourselves and from the operating system kind of level to make sure that we can trust those numbers. So let's do this. And for that, to speed things up, I will have a couple of scripts. So this one, I will start my app, and I will wait for the first successful request. And then I will measure how much time it was used to start my application and serve this first request successfully. So let's go back. Let's kill this one. And let's start my app. And I will use this little switch to switch between JVM and native execution modes. So this says that my application has started, and it also served request, and it printed out my little report. So we see that the time elapsed as observed by the operating system here is 1.2 seconds. That was to start and also to serve this request. So let's see how much it will take in native. So now it's 0.09 seconds. So much faster. But as we said, maybe we don't care that much about startup. Maybe we have a long-running application, and especially if we are in the cloud, so maybe we are rather concerned by how much CPU and memory our application is using. So let's see if we can measure that. And for that, I will also use this nice visual tool called PS Record. So this will look at my process and will output a nice visual chart of my application as a process and how much memory and CPU it is using. So let's go back. And let's do this record, and let's run on a JVM. And this will simulate some load so that we can see how our application performs over time and how it reacts to getting this load and how much memory and CPU it is using as it is serving this load. So now this is done, and we see some metrics, but we are more interested in memory and CPU usage. So let's check that out. And this is the picture that we got for this JVM run. And let's see what's happening here. So we see, so here, the way to read this is that the red vertical lines, that is CPU usage, and the blue horizontal line, that is memory usage. So what is happening here is we see that up until, I would say, 1.5 seconds, we see that there are several more significant CPU spikes, and that is when we are starting our application, and JVM needs to do all of that class loading, interpretation, profiling, compilation, etc. So as we are starting our application, it's quite busy, and it's using some significant resources in the beginning, but also the memory usage is around, I would say, 200 megabytes. And then we see those spikes once in a while. That is when our requests arrive and need to be served. It is still using some CPU to serve those requests when they arrive. So now let's see if we can observe similar behavior for the native application. So once again, we are starting our process. We will send some load to see how our application handles it, and we will see how much memory and CPU it is using. Okay, and we have one more chart here, so let's look at this. And even as we switch between images, you can see how significantly different they are, right? So this one is from our previous CPU JVM run, and this one is our new native process observations. So what is happening here is you no longer see those red CPU spikes in the beginning because we are no longer compiling code when our application starts. It all has been compiled and optimized at build time. We do see some CPU spikes when requests arrive, some of them, but they are not as significant. And in terms of memory usage, if you remember before, it was around 200 megabytes. Now it's 100, but also I think I wasn't limiting here memory in any way. So if I wanted to, I'm pretty sure I could have went very low here, even on something like, I don't know, 16 maybe megabytes, and it will still be operational. So this is how much less memory and CPU our app is using if it's in the native mode. But we all know and love and use Java for high-load applications. So let's see how our application can take an actual meaningful load. For that, let's do the following. So we will send some load, and that will be 1 million requests to our application in both JVM and native modes, and we will see how they compare in terms of peak throughput and serving that significant load. And for that, here we are using the tool called Hey, so it will simulate our load, but also it will print out a performance metric for our application. So let's do this, and let's run it on the JVM. So now we are sending this load. Okay, our responses are back. So we see the response codes all look fine. If we look at the latency, we see that the majority of our requests stay within 7 milliseconds, so not too bad. And in terms of peak throughput, what we see here is 103K requests per second. So maybe it's good, maybe it's not. Hard to compare unless you compare with something else, right? So let's compare with native. And let's run this once again. So now we are running against a native application, and we all know that JVM is amazing and unbeatable for peak throughput. So who thinks this will be faster here in native mode? Okay, some optimistic people who thinks that this will be slower in native. Okay, my host is not too convinced about GraalVM yet. Okay, but let's see what the results are that we are getting here. So again, response codes look good. Latency stays within 4 milliseconds now for most of the requests. And peak throughput is 105K requests per second, so comparable but slightly better. So I think this is a very interesting thing to see because I usually speak at Java conferences and all Java developers are convinced that JVM is unbeatable in terms of peak throughput. And JVM is indeed an amazing example of software engineering because it's really great at peak throughput because it has all those powerful tools. So it's executing your code dynamically, it can adapt on the go, it can make aggressive optimizations, it can de-optimize if assumptions were not right. So JVM is indeed perfect for peak throughput. But here what we can see is that with IoT and with native image, you can achieve comparable peak throughput, comparable to the JVM, in addition to all those startup and memory usage benefits that we've seen before. But this is just one piece of the story. So I ran this against a normal native produced by GraalVM application, and I can take this even further. So if I'm really concerned about peak throughput, what I can do is that I have yet another version of this application. It's called here Simple REST Optimized, and that one is built with profile-guided optimizations in mind. So what this means is that native image builds your application ahead of time under a closed role assumption. And unlike a JVM, the runtime hasn't happened yet, so native image doesn't know yet what will happen at runtime and what exactly will be the most executed methods, which types will be called, etc. So unlike the hotspot, native image doesn't have access to this runtime information and cannot adapt on the go to what your application does and what exactly and how exactly it works. So you would think that it cannot optimize as well as hotspot VM because it doesn't have this runtime information, but there is this powerful optimization called profile guided optimization. And the way this works is that you can build a native executable, then make an instrumented version out of it and run relevant workloads on it so that it can collect profile information of your application. And then this profile information of what your application does at runtime can be fed into native image and kind of give it insight into runtime behavior of your app and let it figure out and optimize your application kind of for the future. So for what will happen at runtime. And this way you can achieve the best of both worlds. So you can still optimize and build your application at build time, but also you can build it in a way that is aware of runtime and optimize for runtime. So let's see if we can make this application even faster if we apply PGO. For that, let me send again the load, and I believe the profile I need is called optimized. So yeah, we are now executing the optimized version of our app. And in the previous run, if you remember, I think we had 105K requests per second. So now this is completed. And if you look at throughput, we have 120K. So even slightly above than we had before, and also above than we had in our hotspot VM measurements. Now, I will not claim that you will always see a significant speed up over running on the JVM, because this is simply not true, and this is just a too simple way to put it. Every application is very different because it's written differently, it's using different dependencies. There are many things in play there. So I cannot give you one specific number of how much faster your application would be if you switch to native image. But what I want to show here on the example of this kind of basic benchmarking web app is that you can achieve peak throughput comparable with the JVM if you're running on native image as well. That is in addition to startup and reduced resources usage. So let's go on and let's see what other things we want to accomplish in the cloud and if GraalVM can help us with those. There is one more interesting aspect of GraalVM and native image that I think is not talked about enough. That's why I love talking about it very much, and that is security. So native image, comparing to running on the JVM, offers you some additional benefits around security, and they come out of the following. So as we said, native image builds your application ahead of time at the build step. And this means that no new unknown code can be loaded at runtime. And in a way, you can see this as a limitation, right? So maybe you want to load new code at runtime. But I would rather see it as a maybe design decision or a different deployment model. And it is a limitation in a way, but it also gives you additional benefits. For example, no new code will be loaded at runtime, so you have more control over your application, and you know exactly what is happening at runtime and which code will be executed at runtime, because native image verified all of that at build time when it was actually building your application. Now, only the code, as we saw before, only the code that is reachable by your application, so something your application explicitly is using, only that code will be included in the native executable. So maybe you are writing your application and you're using many dependencies, and maybe you're not so sure about some of them, and you don't trust them that much. Maybe you're just using a fraction of that dependency, but you're not so sure about that dependency overall. So only the things that you're explicitly using in your application will be included in native executable, and everything else will be eliminated. So if your application is not using that code, it will not be there in the produced executable. And things like reflection and serialization are disabled by default. And again, in a way, it can be seen as limiting, but also I think it gives you more control and more explicit kind of idea of what is happening in your application and what is allowed and what is not allowed. Because for those things to work, you would need to provide configuration, or maybe your framework and library needs to provide configuration, but those things will not happen without you being aware of it. And last but not least, there are some certain attack vectors that are targeting just-in-time code compilation and the compiler itself. So those are simply not possible in native image because at runtime, there is no just-in-time code compilation anymore. It all has been compiled ahead of time. Now let's see if I can demonstrate you how this works in practice. And for that, we have another app here. Where is it? Which is called Unsafe Demo, so please don't try this at home. Please definitely don't try this in production. So what is happening here is this is my application, and under resources here, we have my static folder with this simple hello file. So let's run my app. Let's just see that I killed all the previous processes. Okay, this looks good. And this was, again, a Micronaut application. So let's run it on a JVM. So mn run. Okay, it's running. Let's see what it does and if it works. So it's again on 8080 and it's static folder. So it's supposed to be serving that HTML file that we saw in that static folder. So no-brainer task, it just works, right? But let's see, maybe somebody else joins our team and they decide to implement this logic in a new way. So instead of exposing this file directly, they want to serve this in this get endpoint, and they want to serve this file by its name by appending the static folder and then retrieving the file by the name. So let's say that somebody else on our team came up with that logic. Maybe they came up with it on its own, or maybe they copy-pasted it from some place we all know. So now we have this new logic in our app. Let's see how that works. So the endpoint is now get, and we are serving this file by file name. Okay, this seems to be working as well. But at this point, let me switch to curl to show you a couple more things. So let's curl this. And let me wrap it into quotes, and let's see if this works. So this seems to be working. And also, but we want to make sure things are working correctly, so let's test this. Let's test this in a way that we curl some nonsense. Okay, this doesn't return anything, seems amazing, let's ship it, right? But does anyone see any problem with this implementation? Sorry? Yeah, the room is too large, sorry, I didn't hear you, but the issue with this is that what I can do here is the following. Obviously, this is not a very production-worthy code, but we all made some mistakes in our career, right? So what this opens is the following opportunity. Since I'm not kind of verifying, sanitizing my user input in any way, what I can do here is I can do application.yaml, and this will return me my whole YAML file, including my database config, right? So again, probably not very production-worthy code, but it kind of shows you what could be one possible attack vector. And it doesn't end there. So if I want to spend some time here, or maybe if I know exactly what I'm looking for, I can do something like the following. So example, it's Micronaut, hello controller.class. And I'm not going to print it out, but this would have given me my whole class file. So this is probably not great, but let's see if we can expose the same things in the native app. So again, I have my app compiled over here. It's called Micronaut guide. So let's run it. And let's just check that we killed that one. Okay, seems dead. Let's do it. So now let's run the native app. So Micronaut guide. Okay, it's on. Let's go back. And let's verify the same things. So if we access the file directly, static HTML, static, why isn't this not picking up? Okay, let me try. Hello HTML. Okay, so it gets our message, and if we do the same thing through our get endpoint, get equals get name, was it? Oh, right, thanks. My bad. Yep. Okay, so this is working as well. Let's see if we can expose those config files. So let's go over here, and let's curl our application YAML file. It gives us nothing. And if we curl our controller class, it also gives us nothing, because all those files are no longer there. It all has been processed and compiled into native executable. So accessing those files like that is simply not possible with native image. Okay, so that was talking about security, and also let's briefly talk about packaging size and how native image can be helpful there. So what you get when you build applications ahead of time with native image is you get a simple native executable just as one file, and that includes everything that is needed for your application to run. So your application code, your dependencies code, even relevant JVM code. And all the code that is not used by your application, as we saw just now, is eliminated from your application. Now, kind of a disadvantage that you can see there is that you cannot share the Java runtime installation between the instances of your app, but also it's good in a way because if you want to, you can patch and update your applications individually as you go. And talking about specifically for the cloud and how you can containerize your application, so if you want to really reduce your application image size, you can go really low with GraalVM Native Image. So here the red bars represent still running on a JVM, and the green one that is running on a native image. And if you want, with native image, you can go really low. You can compile it as a native executable, and then you can compress it even further. So there is this tool called UPX, and you can compress a native executable just basically as any other native app. So if you really care about the packaging size, you can go really low with native image and UPX. One thing to be aware of, so if you're doing this compression, it can have runtime impact because it would need to then decompress your app. So it's kind of a trade-off, and you need to choose if you care more about absolutely minimal packaging size or if you want to maintain that good peak performance. Okay, but this may have seemed like a sales pitch so far, so let's talk about what's the catch, because I always get this question, okay, sounds good, but what I need to be aware of, or what is the catch in all this story? So the question would be the following. What about GraalVM and reflection? And I don't know if you've heard it, but sometimes I hear this misconception that GraalVM doesn't support reflection. And that is not true. GraalVM does support reflection, but there are things to be aware of. So one thing is that native image builds your application ahead of time, meaning that it's under closed world assumption, so more dynamic Java features, such as, for example, reflection is a very good example of that. More dynamic Java features pose a challenge because runtime hasn't happened yet. All those things haven't been resolved yet. So it's hard to figure this out under closed world assumption. Native image will try and it will figure out some more obvious, kind of predictable reflection calls on its own. So that thing could be working out of the box. But for things that are a bit more advanced or a bit more complicated, some more help might be needed. And one helpful thing is that native image comes with this tracing agent. So the way to make reflection and also serialization, etc., work with native image is that you would need to provide configuration. And that configuration is coming in the format of the JSON file. So you can write it yourself, but probably writing JSON files, it's not very exciting. So it will be better if that JSON file could be just automatically produced for you. So it can happen indeed, and you can use this tracing agent coming from native image to observe your application behavior on the JVM and produce this configuration file for you. And also, we have this repo on GitHub where we are collecting reflection and configuration information for many popular frameworks and libraries so that you can pull them from this reachability repo automatically and make your dependencies work with native image without any configuration needed from your side. And as an example of that, we also get this question, so how do I know if I want to build my project as a native image? How do I know that my library XYZ will work with native image? For that, we have this page on the website where we have a list of libraries that either provide configuration for native image within the library itself, or it's coming from this centralized reachability repo. So if you're using any of those, and there are like, I think, almost 200 libraries by now, all of those are tested and proven to be working with GraalVM Native Image out of the box. And one more thing, talking about native image and to be aware of or continuing that what's the catch story. So the build time step is more important now because you're performing a compilation of your application at build time step. So you need to be aware that if you're building a larger application, you will spend a bit more time than on the JVM when you are building your app, because there is a lot of work to be done when you're actually building your application. And also, Native Image produces native executable for the target architecture and operating system. So you would need a powerful machine because it needs some resources, but also you cannot cross-compile across different platforms right now. So this is solved a bit in the last release of GraalVM, I would say, because we introduced this native image bundles feature where I can, for example, build a bundle on my Mac. And then if I want to, I can drop it on, let's say, a Linux machine and build a native executable on that Linux machine. But out of the box, something like cross-compilation between platforms is not supported at the moment because we need some JDK-specific features for each platform. And yes, in terms of developer experience and development modes and best practices, we do recommend that you develop your application on a JVM in JIT mode for kind of faster feedback loop, and then you compile to native as a more or less last step in your development process, maybe in your CI/CD pipeline once in a while, but most likely you don't need to recompile your application to native every time you make some minor change in your code, especially around the business logic. Okay, am I running out of time yet? 5 minutes, 4 minutes, okay. Let me see if I can speed up. So what's new in GraalVM? We had this brand new release recently, so this is a huge new feature release on June 16th. So I do recommend that you check it out. We have a lot of new features, and also we have a new distribution of GraalVM, where many of those features that I mentioned, for example, profile guide optimizations, are available in this new distribution. And what's new in this new release, other than that new distribution, is that we now have JDK 17 and 20 builds. So we always encourage you to use the latest. And Native Image as a tool is now included in GraalVM JDK itself. So if you ever run gu install Native Image, you don't need to do it anymore because it is in the JDK. And we now have this build bundle, so you can build like bundle and then easily recreate your build in the future, or maybe recreate it on a different machine, different platform. And we made several improvements to memory usage of the build process and also around developer experience so that you can more easily and smoothly build your applications with GraalVM Native Image. Okay, let me speed up through all of that. So just to emphasize what we will work on next for Native Image, we keep working with many library and framework authors to make sure you can easily use those libraries and frameworks with GraalVM, and you don't need to provide any configuration on its own. We keep working on improving peak performance so that you can get peak performance on Native Image the same or better than on the JVM. We are working to reduce build times, but also requirements in terms of memory of the build process. And we are also working to improve existing GC implementations and add new ones. So to get started, you can go to graalvm.org, or you can use SDK man to easily install GraalVM with just one command. Our latest release is already on SDK man, so you can easily get it from there. So to summarize, what you can accomplish with GraalVM in the cloud is that you can have Java applications that start fast, use very little memory, very little CPU, that are more secure, and also that are very compact and easy to scale. And I mentioned, but also just after the break, there will be also Graham's session where he will talk about Micronaut and GraalVM and how they come together and how you can build great cloud applications with Micronaut and GraalVM. With that, that is all. That is my Twitter handle in case you want to ask questions. And please, once again, the reminder from the organizers, rate this session and ask questions. And with that, that's it from my side. Thank you.